So, hello, my dear students. Hope you are well. Now, today I shall discuss the new chapter. As for syllabus, it is defined as the incompressible viscous flow via finite difference method, which basically we tell computational fluid dynamics. Now, before going to discuss the methodology of CFD, let me give you one preliminary idea on what we do in computational technique. We have, say, as you know, the Navier-Stokes equation cannot be solved analytically with its proper form, which can be solved computationally. Now, the Navier-Stokes equation, if you see there is a PD, partial differential equation, and we know the boundary condition. So, for a given problem, you have the PD along with the boundary condition. So, mathematically, I would say we have the well pushed problem. Then that equation needs to be discretized. Discretized means we shall, convert this PD to a system of algebraic equation, and we know the system of algebraic equation how to solve it. Mainly there are Thomas algorithm or Gauss-Seidel, Gauss-Jacobi. There are different techniques or methods for system of algebraic equation. With that we can solve the system of equation, and then finally we'll be getting the approximate solution of the approximate solution of the original PDE. Here the Navier-Stokes equation. As in the very beginning, I told you, I saw you this, this slide where there are three branches. One study is experimental study. The engineer people who do now mathematician will do either analytically or computationally. The computational here means we shall do it numerical experiment in a virtual flow laboratory. Virtual means in computer. We will not be going to any laboratory. In laboratory in the sense, that doing experiment, we will be doing the numerical experiment in the computer only, which don't define as a computational study. So for that, first of all, you have to define the problem mathematically. For the given problem, you see what the PD, what are the boundary condition, what are the initial condition, then suitable numerical technique and find the solution as I told in the previous slide. Say for example, if you see, this is the continuity equation. This is the Navier-Stokes equation in vector form, and it is also in non-dimensional form. This is a Reynolds compound. And this is the energy equation. Now to solve this, first you have to have a domain, and then you have to solve it. For the domain, as the first step I told, you have to model the problem properly. Model in the sense here set of equation PD and along with its boundary and initial condition. Here governing PD, here parabolic in space, parabolic in time, elliptic in space. For elliptic in space, for that you need the boundary condition at all the boundary involved here. So this is very CFD high level problem. This is the only example for your motivation how we can solve mathematically the Navier-Stokes equation for a problem like flow over a two cylinder. This is a one cylinder and another cylinder, a solid obstacle, fluid flowing over this cylinder. So how can we apply the numerical technique to solve the system of, to solve the Navier-Stokes equation. So I'm not going details here. I shall go for preliminary. The main details there. So this is the boundary condition, initial condition. You define it. So now mainly we shall solve this boundary and initial. This problem, heat equation, heat conduction equation. Very simple equation. del T by del T equal to alpha del 2T by del X square. So this problem is in time, that is in time it is parabolic and space it is elliptic. So for time you need the initial condition. So initial condition is given this one. T of X 0, I mean initially temperature, if I tell you the physically what the problem is here, you have 0 to 1 is the length and this is the equation. 3.1 is the equation. Now for that, initial condition is given and what is the boundary condition? At x equal to 0 for all t, left condition is B, and right at x equal to 1 you have the D. So that means you have two boundary condition, one initial condition, which is the enough. I mean this problem 3.1 equation along with this boundary initial condition problem is well posed. So you have to solve it. So for that there are some set of technique you have to follow, which we define as a numerical methodology. So first is here size of compression domain. What is the size? So for this heat conduction equation, size of the domain is 0 to 1. Now next is grid consideration. What the grid is here? So simply define 0 to 1 with equal number of sides, and then for that we write as a say 0 to 1. Say if you divide it by 10 subinterval, so first is say x equal to xi, put it xi. So that xi is nothing but x0 plus ih. Then you will get the x0 is here 0, 0 plus ih, and if you divide it by 10 subinterval, h will be 1 minus 0 by 10. Then you will get the all the points. That means the whole domain 0 to 1 you are dividing it into small 10 subinterval, and each point you define it as a x0, x1 dot dot xi dot dot x10 here. So 10 if you define it, so in that way if you have 10 subinterval you will have the 11 points. So here this, as you're dividing it into equal subinterval, we should say this is the grid is uniformly distributed. I am telling again, the grid is here uniformly distributed. But for there are some problem where you may have the grid with unequal space. Say for example, very close to the boundary, if you want to take very fine grid, and far from the boundary, you may take very coarse grid. I mean grid size with higher grid. I mean high grid size. So in that case, we shall define as a non-uniform grid. Now, once you have the grid, next question is, how do you arrange the variable? There are two ways to arrange the variable. One is cell center or collocated, other is staggered grid. What is the collocated? Collocated means or cell center. So if you have here only x-axis, I mean 0 to 1, but there are some problem where you have the domain. Domain means in the xy plane. So here only here if you see the problem 3.1, there 0 to 1 or space variable is 1. But if you have more than one space variable, in that case you have to define x-axis by subinterval and similarly y-axis subinterval, and you will see you will have some blocks. Those blocks will be defined as a control volume. So they can be defined as a along x direction if you defined it I and y direction j. Therefore, at a particular, I mean at any general grid, the control volume that we can define or denote as a I, j control volume. Clear? So there, the cell center means at the center you store all the variable. For this problem, you have only, you have only T, capital T, temperature is the unknown. But if you solve Navier-Stokes equation, there you have U, V, P. So whatever unknown or dependent variable, all of them should be stored at the center of the cell. That is called cell center or collocated. It has advantage, easy to code, but disadvantage, pressure coupling between the nodes, it will be difficult. Other is staggered gate. What is staggered gate? Here, variable will be distributed in the sense on the variable. See here. So for staggered gate, at the center you store pressure or any scalar quantity, and on the right, see this is your xj, xi and yj, for example. Then on right side, on the right side means along x direction, you store x component of velocity, I mean u. So this will be u, this is vertical v, and this is p. So u, v, p. That means all are distributed at different places of the cell. That is called a staggered gate. And for this case, very advantageous is very strong coupling between the pressure and velocity. What do you mean by that? See, this is the pressure for this cell, and next cell pressure is this here. And in between, there is a velocity. So this pressure gradient between these two cells will give you the x component velocity. That means del p by del x will give you the u velocity. Similarly, if you see del p by del y along vertical direction will give you the vertical velocity. So this is very strong coupling between the pressure and the velocity. So, but it has some advantages, disadvantages also. Higher order numerical scheme with order higher than second will be difficult. So I'm not going details, that will some higher level. Now, next numerical methodology will come. So if I go back, first we have defined what I discussed. First, size of the computational domain, and then grid consider. That can be uniform or can be non-uniform. Next you come to the, next you come for variable arrangement. Once it is done, you go for the discretization. That I shall discuss later. Once you discretize means you have converted the PD to system of algebraic equation. Then you have to take solution methodology, and after getting the solution methodology, you will have the solution. But keep in mind, solution, once you're getting the solution, that solution you have to check whether that is feasible or infeasible solution. In that case, there are some parameter, numerical parameter, we call here boundary condition, domain size, grid size, CFD condition. This is the one condition in CFD people use to check whether the process is correct. So these are some numerical parameter by which one can validate the code. Code means you have system of equation. To solve it, you cannot solve it by hand. In that case, you have to write a programming that we call as a code. Therefore, that code, see, once writing code, once you run it, you may get some debugging error. Once debugging error is free, so your program or code is ready to give you the output. Now that output, how much is accurate, that you have to justify. So these are the numerical parameter by which CFD people, they do check their code. So now let us come the discretization part. You see, the way the discretization is performed depends on the whether time dependent variable, because once PD, we have more than one independent variable. We define the two. One is time variable derivative, and is spatial derivative. Time derivative, that usually almost everybody discretize it by finite difference method. But space derivative, x, y, z, they can be discretized by either finite difference method or finite derivative method or finite volume method or spectral method. These are the method. Method means this is a discretization method. You can convert your PD to system of algebraic equation. This is space derivative. So that means time derivative you have only one option, finite difference. On the other hand, space derivative you have so many options. So that's what discretizing or the Helen, if you see that converting derivative to discrete algebraic expression. That is the target. Very simple word is discretization means converting derivative to discrete algebraic expression. So as we have seen this problem we have taken for our discussion. So finite difference method, let us take for time derivative only we have option finite difference, but for space you have finite difference, finite volume, finite element. I'm not going others, only I'm taking for the example now finite difference. So if you do here, this is a first derivative, and now look at here, we have discretized it. Time derivative means, okay, before that, first you understand the notation at the very end. TJN. TJN means here you have only X. So that means X direction we have divided and noting by J. So that means XJ. XJ. Now Y direction, the time, so that you take as a delta T. So X direction delta X, Y direction delta T. And notation wise we shall take as N. That means if you see here, TJN is the value of temperature at the JNth node, means Xj at Tn. T means small t. Therefore, and this is your time derivative. So time derivative means you discretize it I mean increment in time. Therefore, see Tj, J is fixed because space no change, only time. Therefore, n plus 1 minus n by delta t. This is your basically nothing but forward difference. Whereas if you see you have del to t by del x square on the right hand side. So that, so n is written here, n is fixed, only j is varied. So j minus 1, j plus 1 by delta x square. So this is, if you see now, no more in PD. This is complete in discrete form. So you are writing the PD in discrete form. This process is called the discretization. So whatever I have explained, that is, see TJN means TJN means approximate solution at the JNth node. And definitely numerical analysis you are doing means there may be some error. See here, one is truncation error because some term has been truncated in the discretization process, and in the solution error, definitely it will be there. So we have to minimize this error. Now, space derivative. So space derivative, there are the different options I shall discuss here. So let me conclude here. Let me put this as a first part, and then because of a space problem, that will consume very huge space. Therefore, let me conclude here. Then I shall send you the part 2 for this